Okay, let's take a look at the warm-up. It says, complete the table by putting a check mark in the appropriate energy change column for each of these chemical reactions. So I want you to read the different reaction types that there are, and then decide if energy is released or absorbed with the people sitting next to you, okay? Let's see what you guys come up with. Okay, what did you guys put for synthesis reactions? Released. How about decomposition? Absorbed. Neutralization. Combustion. Released. Okay. Let's talk about the different sources of energy. So let's come down here. Went too far. There we go. So there are a lot of different fuels that provide us with energy. There's natural gas, wood, coal, and gasoline. And where does energy come from? Most of the energy is stored as chemical potential energy. So it's likely stored in bonds, and we convert that into heat. And the amount of potential energy that's available really depends upon what are the positions of the different subatomic particles relative to each other, and what is the chemical sample made of? Like, what different atoms does it have? And things like that. So anytime we are converting chemical energy into heat, we're going to be using the symbol delta H, which is a triangle H. Okay, so this tells us the energy that's available as heat for any process that we're looking at, and it is sometimes called the enthalpy change. Okay, so H is enthalpy, and enthalpy is the potential energy that can be given off. That's what evolved means. Or absorbed as heat. And it doesn't matter whether it's a physical or a chemical process. If I'm condensing water, that would be a physical process, and there is actually a heat change associated with that, versus if I'm making water from hydrogen and oxygen gas, which is a chemical change, that would also have some sort of an enthalpy change with it. Okay? So regardless of whether it's physical or chemical, it will be symbolized as a delta H with a number after it. So the numbers tell us how much heat energy would either be released or absorbed. Here you're going to see that we have a negative delta H for dissolving potassium hydroxide in water. This negative tells you that this is an exothermic process. So this much heat energy would be released. Okay? If it's positive, like it is down here, where we are melting an ice cube, this positive value tells you that this process would absorb that much heat energy, and so therefore it is endothermic. Okay? Take a look at the next page when you're ready. On the top of the next page, there's a quick check. So with the person sitting next to you, I want you to do it, and let's see what you guys come up with.
Oh, that's
If you're dissolving, like a reactant. Wait. Oh, do the reactant.
would it like the compound have more energy?
So if something is absorbing energy, then now it will be stored. So the products would have more potential energy than the reactants did. But if something releases, that means that the reactants would have more potential energy than the products do. Okay?
Yeah.
Well, replacement, could that also be like formation?
So all of these examples are the delta H's on the previous page. Did you notice that? Okay, just making sure. So you guys, all of these processes, their delta H's are on the previous page at the bottom to help you. The first page that we just went over, at the bottom of the page where they gave you a different process with their delta H values, use that to figure this out. Does that make sense? Okay, dissolving potassium hydroxide, was that a positive or a negative delta H? Okay, so that meant it was exothermic. So do the reactants or the products have more stored energy? The reactants would. Okay, combustion of propane, positive or negative delta H? Okay, so the answer here would be reactants. Melting ice, positive delta H. So it's absorbing heat energy, so now it will be stored in the product. So products. Okay, replacement of iron by aluminum. Negative delta H, so that means reactants. And then forming calcium hydroxide is negative delta H, so reactants again. Does this make sense? Okay, is this a lot easier than what we were doing? Yeah, in section 4.2. Okay, let's talk about the energy of chemical bonds. Let's come down here. If your textbook fell off your desk and I was talking about the potential energy that your textbook has on your desk versus on the floor, because your desk is a higher position, it would have more potential energy on top of the desk than it would on the floor. Okay? Like if you were running up Camelback Mountain and you were at the top of Camelback Mountain, would you have more potential energy at the top or at the bottom? At the top. Okay, so potential energy is also related to position. And when we're talking about the potential energy that has to do with the subatomic particles, we're going to be talking about bond energy. So chemical potential energy is also known as bond energy, and this is related to the electrons in an atom and the positively charged protons in the nucleus. Okay? Bond energy would be an intramolecular interaction. So this term intra, this is referring to things like covalent or ionic bonds. Okay, so these are formed between atoms inside of a molecule, and they're really, really strong, okay? There are weaker interactions between molecules, and these would be intermolecular forces, okay? So intermolecular forces would be things like hydrogen bonds. Even though they call them bonds, they're not as strong as covalent and ionic bonds, right? Covalent and ionic bonds are formed by either sharing electrons or transferring electrons between atoms, whereas hydrogen bonding would be the interactions between positive and negative ends, so to speak, and I'm simplifying it greatly, of a molecule, okay? Now, if we're talking about bond breaking and bond forming, if you're breaking a bond, it's going to require energy. Just like if I break a piece of wood, if I karate chop a piece of wood, wouldn't that take a bunch of energy on my part? So bond breaking requires energy input, okay? That means bond forming, which would be the opposite, results in energy being released. If you're absorbing more energy to break bonds versus releasing more or less to form them, that's going to determine whether you have an endothermic or an exothermic process. So let's come down here. Let's highlight a couple things here. When you have a positive delta H, it's an endothermic reaction, as you saw. And what's happening is more energy is absorbed as bonds break than is released as bonds form. Okay, so that's how you know it's endothermic. And then if you take a look at the top of the next page, we can display potential energy on a graph. You should know what each axis is labeled, and you should know what the general curve looks like for an endothermic or an exothermic process. So this figure right here is showing you potential energy on the y-axis and reaction proceeding on the x. Make a note that this is not time. You will never have time written on the x-axis. Here you can see we have a positive delta H. That means we are absorbing heat energy, and that's why the products have more potential energy than the reactants. Okay, so this would be a potential energy diagram for an endothermic reaction. It will always look the same, okay? If you take a look at the other potential energy diagram underneath this, that one is for an exothermic process. Each axis is labeled the same. The only difference is that you have a negative delta H. So if you come down here, here you've got your potential energy on the y-axis, the reaction proceeding on the x-axis. Notice your delta H is negative. This is the potential energy diagram for an exothermic reaction. Here you will notice that the reactants have more potential energy than the products. Yeah.
Which one would be bonds breaking?
So bonds break in the reactants and they form in the products, so to speak. So you mean which one, like where would that happen?
Which? So,
Hold on.